Hello and welcome back. Let's take a look at some more examples with u-substitution. So again, what we have here is something that is a little bit hard to take an antiderivative of. We've got an x divided by x squared plus 1, so there's a little bit complicated fraction here. But what I'll point out is that if we start replacing some things with u's and make the correct substitution, this will actually be a fairly straightforward antiderivative to take. So here, when I look at this, we're going to have to replace some function here with a u, and we also want to replace this this differential dx with something involving a u as well. So we could try to make this entire function, this du, this entire function, this entire fraction, x over x squared plus 1u. And what you'll notice is that if I were to try to do that, I'm going to have to find du by taking the derivative of that, and it won't quite work out. The trick here will be to take the x squared plus 1 and call that our u. And the question is, how do I know that this is going to be the correct u? Well, it leaves me with an x and a dx. And when I look very closely at what the derivative of u is going to be, if I bring down the 2, it'll be 2x. The derivative of the 1 is going to be 0, so I don't have to add anything. And then for it to be a differential, I'll add the dx at the end. And now, so the reason that I spotted x squared plus 1 as the correct u sub is because now I've got my x squared dx here. And I have my x times the dx right there. So let's rearrange this just a little bit. So this is going to be the integral of 1 over x squared plus 1 times x dx. And again, all I did is I moved the x out of the fraction. And now it's a little bit clearer that, oh, I have my u on the bottom of this fraction, and what is nearly du at the back of the fraction. But I think the only thing to remember is that, oh, I've got this 2 here. So if I want to write x dx there, I have to move the 2 to the other side, so it's going to be 1/2 du. So I can make that substitution. This is going to be the antiderivative of 1 over u, and then x dx is going to be 1/2 du. So we're multiplying everything in here. So, okay, let's take the antiderivative. The 1/2 can just pop out because the antiderivative of anything times a constant is just going to be the constant pulled out times the antiderivative. And the antiderivative of 1 over u is the natural log of the absolute value of u. And that's just something that we have to remember. 1 over x, the integral is going to be the natural log of the absolute value of x. The integral of 1 over u is going to be the natural log of the absolute value of u. And again, we're not quite done because, well, 2 reasons. One is I've taken an antiderivative, so I've got to have my plus c, something I will always forget, but hopefully remember by the end of the question. And the other thing is that I'm taking an antiderivative with respect to x, not with respect to u. So I shouldn't have any u's in my final answer. I should only have x's. So this is going to be 1/2 times the natural log of the absolute value of x squared plus 1 plus c. The other nice thing, which I'll only mention in passing, is that x squared plus 1 is always going to be a positive number. X squared is always going to be positive, or at least 0, because when you square a number, the negative signs will cancel out. And if we add 1, I mean, that's only going to make it more positive. So the absolute value signs aren't really necessary here, because this is positive, but the absolute value of a positive number is positive, so it doesn't affect anything if we have the absolute value signs here or not. It's good to have them in general, though. So there's an example. Let's do one more example, and maybe here it's a little bit more obvious what the correct u substitution is going to be. We've got the square root of x to the 6th minus x to the 5th times 6x to the 5th minus 5x to the 4th dx. So again, we want to find a u sub, so we'll need to know what u is, we'll need to know what du is, and again, u is going to be some function, du is essentially going to be the derivative of that function. So when we stare at this, do we see a function in here, but also its derivative, but also the du, the differential part of it? Well, I think the answer is yeah. We've got a function x to the 6th minus x to the 5th, and we also have its derivative sitting out here. So looking for things and noticing that their derivatives are also in the antiderivative is going to be very helpful. So here is our function that we'll replace with u. The antiderivative, or sorry, the derivative of this function to find the differential, 6x to the 6th becomes 6x to the 5th, minus, and then x to the 5th becomes 5x to the 4th. But if we're talking about a differential, we've got to have our dx at the end. So we can make this substitution, and all the x's will disappear. We'll replace them all with du's. So this is going to be the antiderivative. We've got the square root of x to the 6th minus x to the 5th, so this is going to be the square root of u, times, and then when we look at this, we have our entire du at the back. We've got 6x to the 5th minus x to the 4th, minus 5x to the 4th dx, and all that is just du. Cool. So the antiderivative of the square root of u, well, this is going to be the antiderivative of u to the 1/2. I think it's always easier to rewrite square roots as exponents when we are taking derivatives and antiderivatives. And this will raise this to the 1 higher power, so this is going to be u to the 3/2. That's one more than 1/2. And we have to divide by 3/2, which is going to be 2/3. Again, oops. Dividing by a fraction is the same thing as multiplying by the reciprocal, so we'll just multiply by 2/3. And we can't forget our plus c. So here's our final answer, right? No, because we're taking an integral, taking a derivative, or sorry, antiderivative with respect to x. So our final answer should be with respect to x. This is going to be 2/3 x to the 6th minus x to the 5th, all raised to the 3/2 power, plus c. So u substitutions are, in general, if you find the right u sub, the antiderivative is going to be fairly straightforward to take. It's finding the correct u substitution that requires a little bit of practice. My strategy is always to identify a function that I can replace with u, so that its derivative also shows up. And then we just have to make sure that our new antiderivative doesn't have any x's in it. Now we have an antiderivative that's just in terms of u. So I think more examples is going to be better. So here I've got an example where I have a definite integral, meaning I have bounds on my integral. So let's try to do this, and then we'll have to actually evaluate this integral. So I've got e to the y over 1 plus e to the y power dy. So here we don't have dx, but we can still make our u substitution. We can still plug in a u and a du, and what I want to do is get rid of all these y's in here. So what I want to do is I want to look for a function that I can plug in as u, so that its derivative is also popping out of here. And well, we've got e to the y, so I know the derivative of e to the y is e to the y. That's always a nice fact. So I do have another e to the y. So why don't we call the bottom of the fraction u? The derivative of 1 plus e to the y, derivative of a constant 1 is always just going to be 0. The derivative of e to the y is going to be e to the y. And I can't forget that it's a differential, so I'll get e to the y dy. And again, just to make this a little bit more obvious, I can pull the e to the y out. This is going to be e to the y dy. And hey, look, I can replace this with a u, and so this is going to be the integral of 1 over u, and this is going to be du here at the back. This is our differential. So let's plug this in. This is going to be the integral of from 0 to 1 of 1 over u, and then e to the y dy is our du. And just like before, we had an integral of 1 over u, so this is going to be the natural log of u, and we're going to evaluate it from 0 to 1. Now here's where I want to point something out. What is 0 and what is 1? Well, they were what we had originally used in our original function with y. So we're taking this integral from y equals 0 to y equals 1. So it's important to remember that it's going to be y equals 0 up to y equals 1. Because u is not the same thing as y. So when I'm going to evaluate this integral, I have to remember to plug back in for u my original function, because if I plug in 0 and 1 in for u here, it's not going to make sense. For instance, the natural log of 0 is undefined. It's just like dividing by 0. The natural log of 0 is not a number. So that would be one indication that something had gone wrong. And the reason it would go wrong is because we hadn't substitute our original function back in. So now we can plug in y is equal to 0 and y is equal to 1 into here. So if we plug in 1, we get the natural log of 1 plus e to the first power, which is just e, minus the natural log of, if I plug in 0 into here, so this is going to be 1 plus e to the 0 power. And just to be a bit silly, let's simplify this. So I'm taking logarithms and I'm subtracting them. So this is going to be the natural log of 1 plus e divided by this guy, because when we subtract logs, they turn into the log of the quotient. We just divide their insides. And then e to the 0 power is also 1. So 1 plus 1 is 2. And here would be our final answer, for instance. Okay, so that's a little bit messy, but again, we just see what we want to replace with u, and then replace the differential at the end, and the rest of it is just remembering to plug in our function before we evaluate. And I will do another couple of examples in one final video.